So for this learning module, we'll review how to apply free body diagrams in two-dimensional static analysis. Just as a reminder, your book calls this ideal the analysis of coplanar force systems, meaning that all of the forces lie in a single plane, so the analysis is reduced to two dimensions, even though the system actually lives in the real three-dimensional world. So just to provide some motivation of why we're doing this, remember that statics is kind of one of the tools that we have at our disposal that's a sort of back of the envelope type analysis. And the questions that it allows us to answer are questions that are similar to what's described in this text. So assume that you have this load, which has a mass of 40 kilograms, and you're trying to support it under the geometrical constraints that are presented to you in the world around you. So say, for example, you can only kind of tie in your support structure to the points in your surrounding, points B and D. And you choose to do it with this configuration here, where you have three cables, which are joined kind of in an O-type fastener in the middle of your support structure. And someone comes to you and they say, hey, this mass is 40 kilograms. Here's the geometry of how we've configured it. We're using this kind of cable. Is that cable good enough, right? Because that cable will have some sort of rating in terms of the maximum tensile force or the maximum amount of tension that it can be under. So the question is, do we have tools at our disposal in order to be able to compute what that is? And as engineers, we always try to take the simplest approach first, and this back of the envelope kind of static analysis is the most simple approach that we have at our disposal. So how do we do this? Well, the idea of free body diagram-based analysis is we want to take and isolate a body in our scenario upon which all the forces of interest or that contain the quantities that we want to compute, in this case, the tension in those cables, are included. So if you think about it, if we were to just draw a free body diagram of the mass itself, that would give us part of the information we want. From that, we would be able to determine the tension in the cable connected from point A to the actual load. However, it wouldn't give us all of the information that we want. However, if we focus in kind of on this ring in the middle, the ring in the middle is being pulled on by all of those cables. And as we'll show in a minute when we go to our dot cam, the pull that each of those cables exerts on the ring is equivalent to the tension in each of those cables. So if we were to isolate our analysis on the equilibrium of the ring itself, because one of the big ideals in static analysis is if the entire system is in equilibrium, then each little piece and part is in equilibrium. So if we do a static analysis on the ring, we will be able to determine all of our forces of interest. So I'm going to go, before I go to the dot cam, and I just want to make sure that I have that up. I do. That's good. I want to show some more drawings on the slides. So key point here on the left, what we were trying to say is, if we take our entire system and we kind of cut away the ring and a portion of the cables that are acting upon the ring, we're going to be able to have a free body diagram analysis system that contains all of the forces of interest to us, which are the tensions in those three cables. Now, as we'll see in a minute, when we perform this type of analysis, we're inherently limited at the amount of equations that we have available to us. In a two-dimensional or coplanar system, where we're dealing with the statics of particles, which we'll define more clearly here in a minute, we can only write two equations. So because of that, we only have the capability to solve for two unknowns. So what that means practically is that when we draw our free body diagram, we want to be sure to identify as many knowns as possible. Since the free body diagram involves forces are vectors, those knowns involve both the magnitude of the vectors along with the direction. So we want to capture any of that information we can. In addition, kind of reflecting back on the first portion of our lecture for Chapter 3, we want to kind of build in any physical intuition that we can as well. What do I mean by that? Well, remember that the forces that are supplied by a cable to a body are directed along the axis of that cable. So what that means is we know for these three cables, particularly for the cable from A to D, that the direction of the force will be aligned along the cable. So it will be from A to D. And given the geometry that we have, if we set up our traditional X, Y, or Cartesian coordinate system, that force will be directed purely along the negative x-axis or in the negative i-hat direction. Similar ideal for the force that's exerted by cable AC on the ring. We know that it's purely in the negative y or negative j-hat direction. So that kind of reduces the unknowns associated with that particular, let's start with TAD. We know the direction, but we don't know the magnitude. So we have one unknown there. In addition, I'm going to go skip around a little bit and go to the force exerted by cable AB. If you notice in this scenario, we know that it's kind of inclined 30 degrees from the horizontal. So if we were to know the magnitude, we could decompose it using the known geometry here. So we have one unknown, two unknown. Are we going to be okay? Well, yeah, it turns out we are, because we actually know the tension in this cable by something that I'll show you here in a minute. But the next question that you may have is, well, clearly that ring, it has some dimensions to it. Do I have to analyze this as a body and actually consider those dimensions? Or am I able to simplify my analysis to kind of a particle-based analysis? And reflecting back on what we talked about at the beginning of chapter 3, if I were to extend out the line of actions of all these forces, notice that each of those line of actions passes through a common point at the middle of that cable. So because of that, I can actually treat this as a particle problem and ignore the physical dimensions of my body under analysis. And what that allows my free body diagram to become is just a drawing that has a bunch of forces acting upon a point. That's the ideal of what really makes this particle-based analysis so simple. And just to kind of reemphasize the point, we can do that because all of the forces acting upon our body of interest, which is the circular connector at the middle of the cables, are concurrent. The one thing I wanted to show, and kind of going back of the point I'm going to hit on here, is how we can determine that the tension in cable C, or the force exerted by cable C on the ring, is equivalent to that 392.4 newtons, and what actually that is. So when we have that ring here, right, and let me zoom in a little bit, and we're assuming that this cable pulls the ring to the left, the cable which is ultimately connected to the load pulls the ring down, and the cable that's connected kind of at this 30-degree angle relative to the horizontal pulls the cable in this direction. We might wonder, why is this the weight of the load? Well, what was the idea of weight? Well, let's refresh that first. Remember that in chapter 1, we defined the weight of an object as being equal to the object's mass times the acceleration due to gravity. And by Newton's law of gravitation, technically this varied as a function of the mass of the object that was being enacted upon, along with the physical separation of the object to the center of the Earth. But we're going to approximate that as constant for all of the problems that will work in statics. If you move on to dynamics, there will be scenarios where we'll allow that to vary somewhat. So this is just going to be a constant of 9.81 meters per second squared. And recall back to the chapter 1 content. If you have a mass in kilograms and you multiply by an acceleration in meters per second squared, you'll get a weight in newtons. So this is basically the force that's exerted on any particle of a known mass by the Earth due to gravitational attraction. But the question is, why is that the weight? Well, remember that idea that I said, if an entire system is in equilibrium, that means each of its pieces and parts is. So let's kind of use Newton's law again and focus on the fact that really what we had here was a cable. And we know that back to our earlier chapter 3 material, the cable can only support tensile forces. So here's our cable. And then we had that load here as well. So what actually had the weight? Because remember, as we mentioned earlier in chapter 3, we're going to assume that our cables don't have any weight to them. Well, the load actually had the weight, right? But in order for this entire system to be in equilibrium, if the weight of the load is pulling in the downward direction, then the cable must be pulling that load in the upward direction. And for this to be in equilibrium, then the magnitude of these two forces must be the same. By Newton's third law, if the cable pulls the weight up, then the weight pulls the cable down. In order to be in equilibrium, if the cable is in tension or being pulled down by the weight by W down, then the amount that the O-ring is pulling it up must be W as well. And then again, by Newton's third law, if this force is W, we have the reaction force, which is equal in magnitude in opposite direction, which is also W. So the key point of me going through that is to show you how you can assume that the actual force exerted upon this ring is the weight of the object. It's kind of like it's transferred up through the force system here. So in this case, right, we've said why we can do particle analysis because all the forces are concurrent. We've said that we know both the magnitude and direction of this force. We compute it as the mass times the acceleration due to gravity. We have an unknown magnitude, but a known direction for the force exerted by this cable, which we're denoting as FD. And in a similar fashion, we don't know the magnitude of this force, which we're denoting by FB, but we do know its direction. So fortunately, we have two unknowns, and under the conditions of equilibrium, recall that what they are is a vector-based equation. It says that in order for, in this case, a particle to be in equilibrium, the resultant force as a vector must be equal to 0. And in order for a vector to be 0, each of its components must be 0. So if we just compute the x component of the resulting force acting on this particle and the y component of the resulting force acting on this particle and set it equal to 0, we'll have two equations that we can use to solve for our two unknowns. Well, physically, what is going on here? Well, in the horizontal direction, whatever the x component of FB is, pulling to the right, it must be counterbalanced by the force pulling to the left of FD. We can decompose FB into its x component by just taking the magnitude times the cosine of 30. So that's what this equation says here, that the x component of FB pulling to the right offsets the force FD in our free body diagram. In a similar fashion, what is actually counterbalancing the weight in the horizontal direction? Well, in the vertical direction, I should say. It is the y component of FB, which we can determine by decomposing FB into its y component, magnitude times sine of 30. That's what that term right there is in the equation. So that upward pull of FB must counterbalance the weight, which of course we've denoted as FC. So one term that I wanted to make you aware of is this type of system is said to be statically determinate because the number of unknowns that we need to solve for is supported by technically the number of linearly independent equations we have. So you might recall back to your linear algebra courses that having two equations isn't necessarily good enough. They have to be unique pieces of information, which means that they're just not linear combinations of each other. They're not, if we were to plot them in a plane, they're not two parallel lines. So if a system is statically determinate, it basically means that we can solve for all of the unknown reactions that are keeping the system in equilibrium, which in this case was the tension in each of those two cables. So hopefully that provided you with a little bit more insight. I'll go into this. One of the things that I should mention is this system of equations. Technically, when you have two equations and two unknowns, there's a bunch of different ways you can solve them. You can solve them by substitution, elimination. You can solve them by graphical techniques, or you can use general kind of matrix algebra approaches. In the next learning module, I'll show you how to use a matrix algebra approach. This one was pretty easy because if you think about it, naturally the equations are a bit decoupled. If you go to the vertical equilibrium here, since you know FC, you can solve for FB directly. And once you have FB, you can substitute back in to your horizontal equilibrium equation and solve for FD. So when the equations are a bit decoupled like that, the solution becomes a bit simpler. But when you don't have that situation, I think that it's best to take advantage of the technology we have at our disposal and use linear algebra techniques.